Okay. Hello, everyone. This is our last lecture. And as you know, Monday is your third exam. Now, in the previous lecture, we introduced complex power. And this is the fundamental equation that we have for complex power. Okay, so the fundamental, the definition of complex power is V tilde I tilde conjugate, and we can write it in polar form. And you remember that the magnitude of complex power is called apparent power, and the phase or the angle is called power angle, which is known also as theta s. Also, we can write it in rectangular form, P plus J cube. Well, P is the real or average power, and Q is the reactive power. And you see all the units, and you also see the power triangle. The horizontal distance is P, the vertical is Q, and the distance from the origin to the complex power point is the apparent power. And of course, the angle is the power angle. Now, we're going to define something called power factor, or PF. And it's defined as P over the apparent power, or P over the magnitude of complex power, which is called the apparent power. Now, if you look at this guy, the power triangle, as you can see, this is P, and this is apparent power. Now, is it obvious that power factor is always between 0 and 1?
What's power factor again?
Power factor is P divided by apparent power. It's the horizontal line divided by hypotenuse, right? It's always between 0 and 1, okay? And can you, based on this triangle, give me an alternative equation for PF? So P over the apparent power is equal to cosine of theta s, right? So I can write another equation for power factor, which is PF is equal to cosine theta s. Both of these equations are important, and let me make sure that these are provided to you. Yes, here, as you can see. Both of them are given to you. Okay, now, what is the meaning, what is the importance of power factor? Well, if you remember from the previous lecture, the only element that can absorb P is a resistor. And inductors and capacitors only receive Q, right? So, and if you remember the average power that we calculated for capacitors and inductors, they are sometimes supplying, sometimes absorbing, because sometimes it is positive, sometimes it is negative. For our appliances, whether residential or industrial, we prefer all the power that is being delivered to be in the form of average power rather than reactive power. Reactive power is not exactly desired for our loads, okay? And power factor is a measure, or is the portion of apparent power that is being transferred to our load as a real or average power. So this is basically what power factor means. The portion of apparent power that's being delivered as the real or average power. Remember, real power is referring to average power. Now, based on that discussion, can you tell me what is the ideal value for power factor?
1.
1. Because you want them to be, you want your P to be exactly equal to apparent power, and that will make the angle 0, hence the cosine is 1, right? Or if you want to just more intuitively talk about that, you want all of the apparent power to become average power. So they are equal, so the power factor is 1. Okay, now let's talk about some load, for example, ZL. It has a voltage across it and a current is flowing through that ZL. Now, is there any relationship that I can write between these three parameters, ZL, I, and V? If yes, what is that called? Ohm's law. So I can write V tilde is equal to ZL times I tilde. From here I can write ZL is equal to V tilde over I tilde. V tilde and I tilde are the phasor, or they are the RMS phasors. So I can write V RMS with the angle theta V divided by I RMS with the angle theta I. Can someone tell me what is the angle of ZL? Why 0? First of all, let me ask you this. Do you understand what theta of ZL mean? The phase of a complex number that is given to you as the ZL. ZL is a complex number and it has a phase. That phase is called theta ZL. Now, if you look at this equation, this division, how do you calculate the phase of the fraction, the angle of the fraction? Angle of the numerator minus angle of the denominator, right? Theta V minus theta I. And what do we call that? Theta S. So what does that mean? It means that the resistive, inductive, or capacitive nature of the load completely determines power factor. Power factor is the cosine of theta S, right? So whatever load you have, based on the information given to you by the load, you can completely determine the power factor because it's just the cosine of that angle. I want you to remember this. Theta S is exactly equal to the angle of the load that you are dealing with, okay? Now, let's talk about different cases of theta S. So, first of all, do you remember the ideal case that I asked you about, where P is equal to apparent power? What is the angle? 0. So that's why the apparent power is exactly equal to P. What is the cosine of 0? 1. So power factor is 1. We call that unity power factor. This is the ideal case. Now, if you look at this plot, this diagram, can you tell me what is the load made of? Only resistors. There is no inductors or capacitor involved in it because it's only on the horizontal line, okay? So what is the load? Purely resistive. Yes, yeah. But the overall, remember, consider it inside the black box. The effect that you're sensing, it's not telling you there is a capacitor or inductor. There might be, but they are canceling each other. Okay, so that is the first case. The second case, you have a complex power that is in the first quadrant. Now, is it the ideal case? No. What is the value of power factor? Between 0 and 1. Now, if you remember, if we had, let me just do this. If we had only the horizontal part, it would be a pure resistive load. What if we had a vertical complex power?
It'd be completely reactive. Or like it'd be
Complete?
complex or imaginary.
Yes, it's purely imaginary. But what can you tell me about the load if it is vertical?
Is it only inductive?
Does it have any resistive part? No. So is it inductor or capacitor? Why? Because it's positive, it's purely inductive. So the vertical is purely inductive. The horizontal is purely resistive. What is that blue one between them?
Both.
A combination of resistors and inductors. Okay? What do we call that? We call that the load is inductive. You might be asking, then what do we call a load that is just inductor? Purely inductive. Okay? Whenever you see the word inductive, it means that it has inductors and resistors. Okay? And theta s is between 0 and 90 degrees, and PF is between 0 and 1, obvious. We already talked about 90 degree, but let me point out something else. So, do you remember by how much the current lags voltage in inductors? 90 degree. Remember, current lags voltage, right? Okay. Now, in any inductive load, always the current lags voltage. But my question is now this: by how much the current lags voltage? Sorry, again?
Theta S minus 90.
Just theta s. Why isn't it 90? I just ask you another question. I ask you by how much the current lags voltage in inductors. You said 90 degrees. Now my question is, in any inductive load, by how much the current lags voltage, and why isn't it 90? Because it's not pure inductor. It has some resistive part. Remember, resistive creates no phase difference. Inductor creates 90. When they are combined, the leading and lagging is somewhere between 0 and 90. Okay? That's why the load is inductive, means that current lags voltage by the angle theta s, which is between 0 and 90. How can we know exactly how much the current is lagging voltage? We should have information about the resistive part and reactive part of the impedance, so we can determine that.
That's when you just get ZL.
Sorry?
That's just when you do ZL or Z effective.
We don't have, what do you mean Z
Well,
effective?
if you get the combination.
Yes, if you have the combination of them, then you can find exactly by how much I lags V, okay? Which is the theta SH. Now, I want you to memorize this. This is just an expression. From now on, whenever you see lagging PF, what kind of a load it is referring to? Inductive load, okay? Can it be also purely inductive? Yes. Purely inductive is also considered inductive, okay? The only difference is that you know that exactly it is equal to 90 degrees. Okay, we already talked about when theta is equal to 90 degrees that it's purely inductive. The next important case is this. So what kind of element provides you with a complete horizontal line?
Resistant.
Purely resistive. What kind of element provides you with this guy, the vertical one? Capacitor. So this case is a combination of resistors and capacitors. What do we call that? We call it the load is capacitive. And exactly opposite of that, instead of calling it lagging PF, we call it leading PF. We will do a couple of examples today, and you will see when you can use this concept in your problems. Okay. Just one thing that I want you to remember is that whenever we're talking about power factor and leading and lagging, the convention that we are using here is that we talk about I and then V. That's why we can stick to lagging for inductors. Am I making sense? So we say I lags V because you know that depending on which one you say first, we can also use leading and lagging and different angles. But we stick to I first and then V, and we always talk about the smallest angle between them, okay? This is what we established lectures ago. And finally, if it is negative 90, it means that your load is purely capacitive. Okay, let's do an example and see what happens. Find the complex power that is supplied by the voltage source, and then find PF. Okay? Preston, you ready? Okay, so first of all, I want to find the complex power. What should I do?
Could you find the total impedance?
Yes, and then from that, what do you want to find the total impedance?
Why? You want to find the total impedance? Because you want to find the lag of the current?
Sorry, I didn't hear that.
The lag of the current?
Okay, let me actually ask questions step by step. First of all, when you see the word power, what do you immediately think of? Voltage and current. Now, can I just stick to either of them, one of them, and go for the formula sheet or no? Why not? Because it's a voltage source. It's not a resistor, it's not a inductor, or it's not a capacitor. Okay, it's a voltage source. Okay? Unless you combine the load and treat it as one single load, then you can do it. So, because it's a voltage source, I need both voltage and current. Which one do I have already? The voltage. So, I need to find the current. How do you find the current? Ohm's law. Divide Vs by the equivalent impedance, which is Z1 plus Z2. Sorry, this is I. Let's call this IS. My next question, Chaz, can you tell me why I chose that direction for IS?
Because I believe that's because of that's the polytunnel voltage sources. Like you chose also with prior to the gate.
It's because of this. Supplied. Is it making sense to everyone? Because it's a supplied power, so I prefer the direction to be like that so I don't get confused later and forget the negative sign. Okay? So that is IS, and it's equal to 400 with the angle 0. Do I need to change anything into RMS or no?
No.
No, it is already in RMS form. It's equal to 48.38 with the angle negative 14.36 degrees, and the units is ARMS, amps RMS. Now that I have IS, next, look, can you tell me which equation to choose in order to find the complex power? First, let me ask you this. Can I use this or no? Well, not directly, I can't use them. I will explain it later. Then which equation you'd go for?
It would be the one on the left, first from the bottom.
This one?
Yeah.
But this one is giving you P. I'm after S bar, complex power.
Then the one above.
The one right above, right? Not below. What is this? That's apparent power. That's not complex power, right? What is this? Complex power, okay? So you can either use this one or this one. They are the same thing, okay? So S bar is equal to VRMS IRMS with the angle theta S or theta V minus theta I. It's equal to. Luini, what is VRMS? Say it, yes. That's not V.
No,
400. What is I? RMS? With the angle negative 14, right? Right? Do I need to write the angle as well?
Oh, no.
IRMS is just the value, okay? Not the angle. Then what is theta V? Whenever you don't see the angle written beside a number, what's the angle by default? 0. Minus, what is the angle for current? Yeah, negative 14.36 degrees. And it is equal to 19351, 14.36 degrees. And the units is volt amps. Okay? Now, okay, we found the first part. The next red, what is the power factor?
Power factor would be the cosine of that angle.
Yeah, whatever angle that you have here, that is theta S, right? And power factor is just the cosine of that.
0.96.
0.969. Is my answer complete right now or no? It says find power factor, and I'm saying 0.969. Is that considered complete? What's wrong, Jonathan?
You're supposed to be in unit.
No, power angle doesn't have a unit. Yes. If you say that to someone which doesn't have access to the circuit, he won't be able to recreate the circuit because you're not giving him information about whether it is leading or lagging. And I will explain this later in another example. Now, what is it now? Why?
Because it's inductive.
How do you know it's inductive?
Because the angle thought.
Uh-huh. The angle is in the first quadrant, that's why it is lagging. Theta S is between 0 and 90 degrees, lagging PF. Any problem? Okay, now, you remember I asked you which one is the ideal case for our load, which power triangle is the ideal case, and you all told me theta is, if theta is 0, okay? So if I want to make it a little more general, do you agree that a smaller theta s, for example, in the first quadrant, a smaller theta s is actually more ideal than a larger theta s, right? Because the cosine is higher and closer to 1. So that's why we have a concept of power factor correction. Now, before talking about why we need power factor correction, let me compare two different loads, the same voltage source and the same average power, and see what's wrong with lower power factor. Okay? So we have two different loads. You can think of them as two brands of dishwasher. Okay? Two different brands of dishwasher. They are going to be supplied by the same voltage source, and they require the same amount of average power to operate. 120 kilowatts. They both need the same amount of average power. The only difference between them, the good brand has a power factor of 1. The cheap brand, maybe it's great value, huh? has a power factor of 0.6. Now, let's compare them and see what's wrong with the cheaper one. So I've already written the equation for average power, Vrms, Irms, times the power factor. Remember that this guy is the power factor. So let's plug in. P is 120 kilowatts equal to Vrms is 600 Vrms multiplied by, I don't have IRMS, I want to find it. And what is the PF is 1. From here, I can find IRMS to be 200 amps RMS. Also, let's do it for the second load. The same amount of voltage source. Let's add a, no, that's fine. And the power factor of the second one is 0.6. And from here, we see that IRMS is 333 amps RMS. So what's wrong with the cheaper brand?
They have a way more.
So it's drawing more current from the grid. But is it doing anything in exchange for that? No. It's doing the same job for you, right? So for example, you might think that, okay, we can reduce the amount of power that is consuming so to make sure that the current stays at 200. But if you reduce the power, it means that probably your device is weaker, okay? That's why we can say that the higher power factor is, and closer to 1 it's more ideal for our residential or industrial loads. The generator feeding load 1 has to provide 133 amps more current for the same amount of real or average power, which means larger current, larger equipment, larger transmission losses, and higher cost. Okay? That's why we say we are interested in power factor of 1. Now, another question that you might be asking is, okay, why don't we design them in a way that is just resistive?
Because we have to use inductive.
Yeah, fair enough. But the thing is, most of the industrial and residential loads are actually inductive rather than capacitive. And can you tell me what's the reason for that? Because there are a lot of motors, electric machines, there are a lot of windings, coils, okay? And these all create inductive behavior, okay? That's why most of the loads are actually by nature, inductive. Okay, so our power factor is never 1, and now the concept of this part of the lecture is that how can we correct that?
We just add capacitors for fun.
Is it good enough for you? Why?
Because it will, like if you have positive angle, the capacitor will decrease that angle, making it closer.
Okay, I'm very tired. Do you want to continue the rest of the lecture? Because it was very good. I'm not joking. Exactly. I couldn't have said it better. Because you have a positive angle, you want to push it down, pull it down. What element can do this? A capacitor, okay? So yeah, power factor correction is going to be done by a capacitor. Where was I? Now, let's talk about how we can do power factor correction. Okay. So first of all, what do I mean by old here?
Like we say, like that's what we have so far.
Before correction. What we have before correction, okay? Now, if I pull this down to decrease theta s, it will increase power factor, right? So this will be a better power factor. Do you all agree with that? So I'm going to call this guy the complex power of the new case. What do you call this angle? Theta nu. A couple of more questions. So what do you call this value? What P? It's not the P nu? It's the same. Is there any reason why I took them to be the same?
Because we're trying to like make the power we're using more efficient. So we're keeping the power.
Yes, because we don't want the device to consume more average power or less average power. More average power means higher electricity bill, less average power. If the design is not completely revolutionized, it means that you're messing something up. You're probably replacing good parts with cheap parts, okay? So we don't want to mess with the real power or average power that we're consuming. We just want to make the system more efficient, okay? So that is, what do you call this guy? Q old. What do you call this guy? Q new. Now, I want to change the black one into the green one. Not based on your understanding. We established based on what Cameron said that we need to add a capacitor, okay? We understand that. It makes sense because based on the 2D complex plane, capacitor is going to compensate the behavior of an inductor. But mathematically, based on vector algebra, can you tell me why a capacitor should be added to the system to change the black to green? That would make me very happy.
Something to do with adding vectors.
Okay, how do you add vectors, Chaz? You raise your hand.
I was thinking that if you, let's say let's say instead of transferring to the green line, you just move the line down, you would not maintain the same P. It would just become a larger P, which is not really long. But like instead of like, converting the hypotenuse to the length, you try to maintain the power.
See, you completely understand the concept, and it's very good. This question probably is not very important for your course, but I'm curious. I'm curious if you know how mathematically can I change the black one into the green one? Yes.
So you just add the like parts of the, what are they called? So if you have like,
Let me.
X and Y, and another vector of X and Y, you add the X's, you add the Y's.
Yes, but are you trying to add the old one and new one together? What's the point?
No, you have S O and then you have a random capacitor thing.
Okay, yeah, that's the important one. Let me write something for you. I want to go from this into this, right? Based on vector analysis, can you tell me what should be added to the left-hand side? A vector, right? A vector. How do you add vectors together? You draw the first one, and then from the end of the first one, you draw the second one.
Oh, yeah.
Right? That's the vector addition. So do you agree that if I plus red, do you agree that SO plus red one, which let's call it S power factor correction, based on vector algebra, do you agree that if you find the red vector, it will give you the information that you need for your compensation? Okay. Now, what is it red one associated with? Why? Why capacitor?
Because it's negative 90 degrees.
It's negative 90 degree. It's vertical and pointing down. So what element it's related to? Capacitor. Did that make sense to everyone? Okay. And how do we calculate that? First, let me do this. You add a capacitor in parallel with your load, okay? And then if your load is inductive and the value of the capacitor is calculated properly, this will be your new load with a corrected PF.
And would your magnitude of like the reactive power of the capacitor would be equal to the change in reactive power of the load?
Exactly. Yeah. Now, the next part, I used to teach that for first couple of quarter, but there's no use in that on your exam. And if you're kind of person that you are interested in knowing what or understanding when an equation is given to you, this is for you. And it's just 5 or 6 lines. You can easily follow along the line. But what I want you to not even memorize, just understand, is the last equation in a box. What is this equation giving you? Based on all the information about the old circuit and the target PF, which we call the new PF, you can calculate the amount of capacitor that you should put or place in parallel with the old load to correct the power factor. Did that make sense? Okay? Now, what is the ideal theta nu? 0. But sometimes we might not be able to make it 0 for many practical reasons, okay? So don't expect theta nu to always be 0. It is always given to you though, okay? It's always given to you by the problem. What is theta old and P old? They are all the information about the circuit before being corrected, okay? What is omega is the angular frequency. And what is VC tilde magnitude? What is the other name for VC tilde magnitude? VRMS across the capacitor. Okay, that's very important. Now, let me see what I have here. Let's do an example. Okay, so first of all, let me write this is the previous example, exactly. The only thing that I've added is that we want to correct the power factor, okay? So let me write the information that I have from the previous example. So this is what we calculated from the previous example. Is there any appropriate subscript that you would suggest adding to this S? Old, right? Because it's the circuit before compensation. This is the value that we had. 19,351 with the angle 14.36 degrees, volt amps. Who was next? Jonah, you ready? Xavier, can you tell me if I need to write this in the rectangular form too, or that polar form is enough? That's S old. Do I need to write it in rectangular form too, or just that is enough? Why? For what exactly? Look at the green formula, and which parameter in that green formula requires you to have S old in rectangular form as well? No. Do you know generally S is equal to what in rectangular form? P plus J Q. Okay? So which parameter in the equation require you to write S in rectangular form? P old, right? Do you all see that? So, see, this is equal to P old plus J Q old. I don't need the Q old, but I can find the P old. Give me the value of P old, please. I have it actually. It's 18,747 watts. That's your P old. So we calculated P old. Braylon, what is theta old? It's just screaming. Perfect. That guy is theta old. So you can calculate its tangent, right? Do I have it? No. Can you give me the value? I think it was 0.256. Okay, so we have tangent theta old. Omega is very easy. What is omega? 2 pi f, which is 120 pi. What is next? What is VC tilde magnitude? Let me ask you another question. Where do you add the capacitor? Here, here, or here? C1, C2, C3. Which one? C3. Why? Say, yeah, that's correct. Because that will compensate both of them together, the combination of them. If you add C1, which one it will compensate? Only Z1. C2 only compensates Z2. If you want to compensate your whole load, then you have to add C3. So this is where you need to add your capacitor. Now, can you tell me what is the voltage across the capacitor in RMS? 400. So VC tilde magnitude, or VRMS, VC RMS is equal to 400 volts RMS. What else do I need to know? Theta nu. How do I find it?
Inverse cosine of
Okay.
power factor.
So I'm going to write this in blue, and I'm going to box it because it's very important. Theta nu is equal to cosine inverse of power factor nu. Do you agree with that? Give me the value, please. 11.478 degrees. Now, this is your thetas. Please do this for me. Calculate the cosine of negative 11.478. It's the same. So how do you know it's positive, not negative? Because it's no. Your PF is lagging. What does lagging mean? It means that it's in the first quadrant. Okay? So that's why I'm writing this equation in color and adding this sign here. In fact, let me add it in another color. Remember that it should be positive if it is lagging. Now, how do I do the next part? What is it asking? Everything I've calculated holds except theta nu, right? The only thing that I should change is theta nu. So maybe I should just put this A here. Everything is common between them. Theta nu is equal to cosine inverse PF nu. This case, I should add a negative sign. Why? Because it's leading. Because leading means capacitive, and it will end up in the fourth quadrant. And the value will be negative. Oh, there is something left in the first part that I forgot to calculate. Probably the most important thing, but it's the easiest one. So after you calculate all the variables and all the parameters, you should calculate the capacitor. What is the capacitor? It's the last lecture. I'm going to give it to you. I mean, it's just plugging in numbers. Okay, you calculate it, and let's check that my value is correct. No, nobody is willing to.
16.45 micro.
Yes, 16.44 I have. You're wrong. Microfarad, okay? And how about the other case?
142.69.
66. Okay? Done. Just one question. Why is the capacitor for part B is so much larger than capacitor for part A? Let me ask Samuel.
Is it so much larger?
Yes, why is the capacitor in part B so much larger than the capacitor in part A?
Is it because of the much higher PX?
I didn't understand what you said. Next. I'm trying to remember your name. No. Yes, Cannon. Next. Pass.
The question was
Why is the capacitor that we found for the part B is so much larger than the capacitor that we found for part A?
Is it because the capacitor naturally wants to lag, so you kind of have to go all the way around?
Perfect, yeah. So let me just a little polish that, okay? The capacitor not only needs to compensate the inductive behavior, but it also needs to push it into capacitive behavior, right? Because it's in the fourth quadrant. Yeah? Not in the second quadrant, the capacitor pushes it down, and then not only pushes it down to get close to power factor of 1, it pushes it further so that it goes into the fourth quadrant. That's why we need a much larger capacitor. If you were to choose between one of these two designs, which one would you prefer? A or B? Why?
Requires such a large capacity.
Is there any difference between the performance? No. So why bother with the larger capacitor? Sorry?
The weaker capacitor just being like cheaper.
I mean, it's not about just being cheap. Capacitor takes a lot of space, especially if they are very big. Okay? So we prefer A. We call the case in the B overcompensating. We don't need to push it to go to fourth quadrant, right? I mean, the first quadrant is enough as long as the power factor is the same. Okay. Let's go for the next example. Yes. Sure.
If you have a capacitor that's halfway capacitance between cold and heat, would that give you a P factor of 1? Like if you went right in between the...
You mean exactly half them? No. Can you tell me why not?
Because power factor depends on other factors, not just capacitance.
No. Well, let me tell you this. First of all, I'm 99% sure because nobody's ever asked me this question. But I am almost positive that it's not exactly half of those values. And the reason for that is that the relationship is not linear. The only way that it could be half is when it is linear. Cosine inverse is not a linear. It's the most nonlinear thing in the world. Sure. Next example. Okay. A voltage source is given to you with two different loads. Unfortunately, we don't have information about these impedances. We only have some information provided to you. And this is what I'm going to do. Well, this is what you're going to do. Jonathan, what information can you give me about load 1?
It's got a power factor of 0.8.
Okay, so PF1 is equal to 0.8. Lag. From here, can you tell me what is theta S1? What should you do? Do you remember? It's this lecture's concept, so it's fine if you don't remember. But do you remember the relationship between power factor and theta S? Power factor is the cosine of theta S. So in order to find theta S, you need to take the cosine inverse of power factor, right? The only thing that I'm asking you is positive or negative?
It's going to be positive.
Why? Because it's lagging. And the answer is 37 degrees. Very good. Next, what other information can you give me about load 1? Do you see the number 10 kW? What parameter is that? No? Cage. Why?
Because it's source resistance. The units.
Because of the units. See, the only thing that you have the units of, you have it the units of watts is average power. I remember one student asked me, how come you don't know, how come you're sure that it's not instantaneous power? But what kind of instantaneous power doesn't depend on time? So this average power, okay? So P1 is equal to 10 kilowatts. What do I need to find for part A? Seth. I need to find the complex power, okay? You need to remember, S bar is complex power. How can I do that? Let me ask you a question that makes it much easier. What is complex? We have two representations for complex power, right? One of them is rectangular, which is P plus JQ. The other one is polar representation, which is going to be apparent power angle. So which one do you think we should go for? We have P, but we should calculate Q, right? How do we calculate Q? You don't know? Aaron? Sorry?
Don't you need the current?
No, we don't know the current because we don't know the impedance.
Put it into rectangular form for the JQ, reactive power.
Well, we don't have the complex power. We want to find it. We have the P, but we don't have the Q. How would you do it? Jonathan?
You have it in polar form now, right? You need 10 kilowatts and you'll.
No. 10 kilowatts is P. It's not apparent power. So let me put it this way. We need to find what? S, right? S1. So you have two options, either P1 plus JQ1 or the apparent power 1 with angle 1. Now out of these four, you have this guy and this guy. You either need to find Q1 or the apparent power 1. Which one do you want to go for? Both of them are possible. I would prefer apparent power. How? Yep. You remember this thing? That's a power triangle, right? So, do you agree with that? S1 apparent power is equal to P1 divided by PF1. Okay, you're looking at me very mean. Do you agree with that or no? That's a fundamental equation. Huh?
Is PF base,
Sorry?
is PF basically like the results of doing basic technology on that kind of?
Yeah.
That would be, so you're dividing by cosine of
Exactly. You're after what in that triangle?
that hypotenuse.
Hypotenuse. Okay? So just the vertical divided by the cosine. And it's equal to 10 kilowatts divided by 0.8, which is 12.5 kilovolt amps. And from here, what is the final value of S1? 12.5 with the angle 37 degrees kilovolt amp. We found the power, the complex power absorbed by load 1. Let's go for part B. Preston, what information can you give me about load 2?
PF is 0.95 leading.
So PF2 is 0.95 leading, which makes theta S2 equal to negative cosine inverse of PF2, which is equal to negative 18.2 degrees. Okay? That's similar to part 1. Chaz. What is that 8? Yes.
That's your apparent power.
Why not complex power?
It's a different unit, it's kVA.
No. They have the same units. Apparent power and complex power, they both have the units of volt amps. The K is just kilo. So why not complex power? Why apparent power? That's probably the trickiest part of this problem. Huh?
It is apparent power, but you do not apply.
There's no J.
Because it's a real value with no angle. Remember, complex power is a complex number, so it should have angle, right?
Or J. There'd be a J.
Also what?
It wouldn't give it to us because that's what we're finding anyway, isn't it? The complex power.
That's also a good argument. Yeah, it would be stupid to give it to you and ask for it, right? But anyway, I want you to understand it not based on that argument, based on the fact that it is just a real number. What were you?
If they did give us it, it would have a J as well, right?
Not necessarily. They could give it with the angle in polar form.
Gotcha.
Yeah.
The thing was zero. Would it tell us zero?
You tell me what's the meaning of that?
It would be the same. Like, oh, then the complex power would have zero.
No, it's not zero. If the angle is zero, what does it mean?
It would just be one.
It would be only resistor, right? You only have resistor. It doesn't probably, not probably, it definitely doesn't need any correction. Okay, so the apparent power of the second one is given to you, which is 8 kilovolt amps. And so I can say that S2 is equal to 8 with the angle negative 18.2 degrees kilovolt amps. Okay. Let's talk about part D. Where do I want to add the capacitor? Is it good here?
Yeah, it doesn't matter because it's in there.
It doesn't matter, right? But, okay, since it doesn't matter, it's prettier to add it here, right? Okay, now here is my question. That's the equation. I know what omega is. I know what theta nu is. These are easy ones. In fact, let me just move that to here. Part D. I know that I skipped part C. It was intentional. So here's my question. For Luke, it's your turn. Let me copy that here as well because I want you to have everything in front of your eyes. Tell me, what is theta nu? Very easy question. What is PF nu? Read the statement. 1. Okay, so what is theta nu? 0. Very easy. So theta nu is 0. Okay. What is omega? It's obvious. 2 pi times 60. Luini, what is VC tilde magnitude? What is the RMS voltage across the capacitor? No. I won't accept that. It's right there. What is the voltage across the capacitor? You just looking at it. Yes, 208. For the next 15 minutes, forget all your constitutional rights as an American, okay? You can't use any of those amendments. So the last two things, which are very important, theta old and P old. How could I calculate that? Jonah, pass. Braylon. I'm joking. If you're not comfortable, you can pass it. The question is, how do you find P old or theta old? Whatever you want, whichever you want. Just pick one of them and tell me how to do it. You pick pass. Samuel. Will.
Would you combine the complex powers for both of those loads?
Perfect.
in
Yeah.
parallel, and then if you get it in pole, you just translate it to rectangular for P or theta?
Yeah. So, should I just consider one of the load when I'm finding P old and theta old? No. Because you want to, because these are all in parallel. If you only consider one of the load, it's not going to compensate the whole circuit. Okay? Do you see that? C is going to compensate the combination of load 1 and load 2. If you want to, let me actually draw something for you. Probably it's going to be intuitive. So okay? We want to compensate the whole circuit. So how do you find the S of 1 and 2 add them together. I have 18.29 with the angle 15.87 degrees kilovolt amps. Jonathan, should I write this in rectangular form too or no?
Yes.
For what?
Power.
For power, for P. 17.6 plus J 5 kilovolt amps. Okay? Now, do I have everything? What is P old? 17.6 what? Kilowatt. And what is theta old? 15.87 degrees. Did that make sense to everyone? Plug in everything and give me the value of C. Do you have it?
368.82 nanofarad.
300 then?
68.
Oh, I have a different value. Can someone confirm?
What's the voltage? Oh, it's.
I have 306.67. It could be well wrong, my value too. Anyone?
Oh, no, yeah, I did 18.87, not 15.87. Yeah, 306.77.
306.67 microfarad. Okay. Any question? We didn't have time to do the mini lab in the previous section, so we're not going to do it. If you're interested in doing it, you can come on the mini lab makeup day and do it for your own interest or knowledge, but I'm going to give the credit to every one of you for mini lab 7 and 8. Okay? Any other thing?